Hello and welcome to this Spacewalkers live session in which I will present Ethernet ring protection switching mechanisms and associated automatic protection switching protocol. Here is the agenda. We will start with reminding ourselves about ERP definitions and basic mode of operation. After that, we will describe ERP architecture with more details, and finally, we will go over different use cases with ERP deployments. Ethernet ring networks provide multi-point connectivity with reduced number of links. As you can see in the drawing, every ring node is connected to adjacent ring nodes with a single link. Only two nodes can already form a ring, but ring can also be deployed over a long distance, which is typical deployment in transportation networks, either rail and metro or even ITS. Although ring topology requires a single link to be used to connect adjacent ring nodes, it is however possible to deploy switches in virtual chassis mode, so two physical nodes acting as one logical, and use more than two physical links between nodes for increased redundancy. There are also deployments with two separate physical rings of the core network that can work in active-active mode, sharing the network load and services. Since ring creates physical loop, the network is a subject to creating layer 2 loops. Therefore, we need a mechanism or a protocol that is capable of preventing these loops but also be able to react deterministically to a single link or node failure. This reaction and overall convergence should be in range of tens or hundreds of milliseconds, depending on applications running over the network. Standard values for signaling is 50 milliseconds, and for critical applications, 200 milliseconds or less. There are several protocols within our portfolio that fulfill these requirements and could be used in ring networks. We will not compare them in this session, but just to mention a few of them. There is IP/MPLS, a service-oriented technology capable of path convergence within 50 milliseconds using fast reroute mechanism. Then there is a shortest path bridging, which is another service-oriented protocol with fast convergence. And there is also Ethernet ring protection protocol, which is the main subject of this session. All these protocols are suitable to be used in the core of the transportation network. For the access connectivity networks, as usually deployed in stations, there are multiple choices as well. ERP protocol can be deployed as a subring. DHL or dual home link could be another choice. Multi-chassis or MC-lag as well, or LACP to connect a single device with multiple physical links to the core network node. ERP is a standard-based protocol, and many times it will be mentioned as G8032, with the latest version of ITU-T recommendation released in March 2020. Under normal condition, all ring links and nodes are up, and it is on ring protection link owner node to bidirectionally block forwarding over the single ring port. This link is then called ring protection link or RPL. This way, traffic can flow on all but one of the ring links and between all ring nodes. As you can see here, it is also possible for a node on the other side of the ring protection link to block the traffic over its ring port as well. In a case of a ring failure, it is on the ring nodes whose direct connected link failed to block their ports over failed link, and on RPL owner node to unblock the RPL. This way, traffic will again flow through all the ring links but one, the failed one, and among all ring nodes. Coordination of these protection actions over the ring is performed by Ring Automatic Protection Switching Protocol, or RAPS. After the failure is recovered, meaning failed link is up again, by working in revertive mode, the traffic will be forwarding over recovered link, and functionality of RPL owner to block the RPL will be obtained automatically. In non-revertive mode is chosen, ring nodes will continue to block the traffic over recently recovered link. As defined in ERP version 2, Ethernet rings started to support multi-ring or ladder networks that consist of conjoined rings by one or more interconnection points, and some of design examples of multi-ring can be seen on this slide. In order to support multi-rings, the following principles have to be followed. R APS channels cannot be shared, meaning this link that is called interconnection link belongs to main ring only. On each ring port, each control and traffic channel is controlled by a single ERP process and belongs to a single ring. It means that in this case, these two ports are controlled by ERP1 process, and this port is controlled by ERP2 process running on the same node. Also, every ring must have its own RPL. So this is RPL for ERP1 and this is RPL for ERP2. We will discuss in details ERP functionality over multi-rings later on in this session. As defined in the standard itself, ERP is capable of converging in less than 50 milliseconds, but this cannot be taken out of context, or better said, out of standard. In the standard, you will find the specific conditions of the network with respect to ring distance, the number of nodes, fewer than 16, and ring node status in order for convergence to be below 50 milliseconds. So it makes difference if network deploys a single node or nodes connected by virtual chassis, if a single link or link aggregation of two or more links are used. It is also not unusual to have more than 60 nodes in the ring in production networks. It is important to understand it is not end-to-end convergence time of 50 milliseconds or less, and it doesn't include convergence between end user connected to access network and application server, for instance, in the data center, and it doesn't include VRRP convergence within transportation network. All these factors would lead to potentially longer convergence times. Every node participating in ERP ring runs ERP process for that ring. With respect to the ERP protocol, every node has related node ID, unique in the ERP ring, and port ID, unique per node. Based on RPL owner configuration, node number 4 blocks bidirectional traffic on its port with ID 0, which is RPL port to which RPL is connected. Terms control and client channel in ALE terminology refers to service VLAN and user VLANs. Similar functionality is performed on RPL neighbor node. As stated in the standard, protection switching is based on the transmission of local switch status and requests to all ring nodes via the R APS specific information. In this idle state, it is RPL owner informing all other nodes in the network using R APS messages that RPL is blocked on node 4 itself and its port 0. The message includes also code NR, meaning no request. What is also presented on this slide on every ring port is maintenance entity group endpoint map that might be used for continuous monitoring of ring links, as this is not the task of ERP control process. ERP control process enable and disable Ethernet forwarding over the links in the ring, as well as flushing forwarding database of nodes in the ring. It is map that informs ERP control process about detected link failure. The network moves to protection state when link failure is detected. In case of link failure, both nodes, 1 and 2 on our slide, will start hold-off timer. If the link failure clears within period defined by hold-off timer, no link failure will be reported to ERP control process. If, after expiration of hold-off timer, link failure still exists, the failure will be reported to ERP process, which will then block the failed ring port on each node. ERP will also initiate flushing the local forwarding database and will start to periodically inform other nodes in the ring about the link failure via RAPS messages. These messages will use code SF, signal failed, followed with node ID and port ID. So, as seen on this slide, node 1 will send SF messages with node ID 1 and port ID 1. And node 2 will send these messages with ID of node 2 and port ID of 0. SF messages has higher ERP process related priority than NR messages already sent by RPL node, RPL owner node, informing ring nodes to act upon SF messages rather than NR messages during the time both messages are sent across the ring. Upon receiving signal failed message, all ring nodes but RPL owner and possibly RPL neighbor nodes will perform flushing of a local forwarding database in order to speed up convergence times by relearning the correct filtering entries. As already mentioned, ERP relies on Ethernet-based learning, forwarding, and filtering database mechanisms. Upon receiving the first signal fail message from a node in the network, RPL owner and RPL neighbor nodes will unblock their end of RPL and then will also perform a flush of the local forwarding database. As two nodes sent out SF messages as a reaction to link failure, all the nodes in the network will receive another SF message as well, with different node and port IDs. Upon receiving this message, all nodes will perform FDB flush for the second time. Nodes 1 and 2 will continue to periodically send SF messages as long as link failure persists, but other nodes will not react upon receiving them, as those messages will carry node and port IDs already known to ring nodes. The network is now in stable SF condition. On recovery of a link failure, of course, the first nodes to notice that will be nodes 1 and 2, nodes on each side of recovered link. They will clear their signal failed condition and will then start guard timer, during which they will neither receive nor process newly received RAPS messages. They will also start sending their own RAPS messages with no request code instead of signal fail code, informing other nodes about link recovery. Note that nodes 1 and 2 will still block traffic over the ports of recovered link, as they started during protection state. This phase now of the network is called pending state. At this moment, we have a network that is still blocking traffic over recovered link, and nodes 1 and 2 are sending out no request control messages, informing that previously failed link recovered. After guard timer expiration on nodes 1 and 2, those nodes will start receiving RAPS messages from each other with NR code. Node 1 will, upon receiving NR message from the node with higher ID of 2, unblock the port of recovered link. The port on node 2 will still block bidirectional traffic, preventing the network from looping. Upon receiving NR control message, RPL owner node will start wait to restore timer, allowing for time to verify the ring has stabilized before blocking the RPL. After the timer expires, RPL owner blocks RPL port, flushes local forwarding database, and starts sending control messages with NR-RB code, no request, RPL blocked, informing all nodes that RPL is blocked again. At this moment, we have two nodes in the network blocking two different ring links. Upon receiving no request RPL blocked message from RPL owner, different nodes in the network will act in a different way. Node 2 will stop blocking the ring port, therefore link between nodes 1 and 2 will be forwarding traffic again. It will also stop sending its own RAPS messages with NR code, and it will flush local database. RPL neighbor node, if configured, will start blocking its RPL port and will also flush local forwarding database. Any other node in the network, upon receiving NR-RV messages, will flush their own forwarding database. At the end of this process, network is back to idle state, blocking traffic only over RPL link. The process that was just described refers to revertive mode of ERP ring. It is also possible to configure the ERP ring in non-revertive mode. In this case, protection and pending states are the same as in revertive mode. The difference is that in non-revertive mode, RPL owner node will not react on received no request messages from nodes 1 and 2, but will continue forwarding over RPL. The RPL owner requires force command to be executed to continue with recovery process of blocking RPL port, sending no request RPL blocked messages, and flushing local database. Non-revertive mode is sometimes preferred in order to avoid second interruption. It is also possible that link failure will be noticed as unidirectional link failure, in which case only one node noticing the failure, of course, will participate in link failure and recovery processes. Link failure can also occur at RPL. In this case, standard revertive process will take place, but without flushing local forwarding database by nodes in the network, as the same link was blocked for traffic before the failure, so no changes in forwarding database filtering is expected. All RAPS messages in this case of RPL failure will use DNF, do not flush indication. This slide shows multi-ring model of ERP network. According to previously mentioned principles, this multi-ring network has two rings with two RPL owners, one for each ring. This is RPL owner for ERP ring 1, and this is RPL owner for ERP ring 2. Links that belong to ring 2 are links 27, 7.8, and 8.3. Interconnection link 2.3 belongs to ring 1 only and is controlled by ERP process for ERP1. Nodes that have ports in more than one ring are called interconnection nodes. Those are nodes 2 and 3. They are also running two separate ERP processes, one for each ring. Failure of interconnection link triggers protection of ERP1 only, as interconnection link belongs to ERP ring. In this case, RPL owner of ring 1 starts forwarding over RPL, while RPL owner of ring 2 continues blocking traffic over RPL link 7.8. Here, on the right side, you can see logical representation of multi-ring network. You can see that in both idle and protective state, multi-ring networks maintain connectivity between all the nodes in a loop-free logical topology. Interconnection nodes are running as many ERP processes as many rings and subrings they are connected to. In our example, nodes 2 and 3 are running two ERP processes, while other nodes are running only one. Also, each ERP port can be controlled by a single ERP process. So in case of node 2, ports 0 and 1 are controlled by ERP1, and port 2 is controlled by ERP2 process. There are two modes of ring interconnections, with and without virtual channel. In case when virtual channel is used, control channels of subring ERP, in this case ERP2, is forwarding over ring 1 as a fully connected ring. The path of ring 1 through which ERP2 control channels are passing by is determined fully by ERP control process, so control channel of ERP2 is treated as a regular data. If the link between nodes 2 and 3 is forwarding, for control and traffic channels of ring 1, then ring 2 control channel will follow the same path. In case ERP1 process select another logical path for its control and traffic channels, due to link failure between nodes 2 and 3, for instance, then ERP2 control channel will follow the same path. In that scenario, FDB flush initiated for ERP2 interconnection nodes may be used by ERP control process of ERP1, but not the opposite. In case of ring interconnection without virtual channel, ERP2 control channel is not fully connected over the main ring. Therefore, it requires for RPL owner not to block control messages. This scenario could also result in segmented subring. Now let's take a look at ALE implementation of ERP. Configuration of ERP ring is straightforward, and we will use this example to go through some configuration commands. Using a single line command, a network administrator defines ERP ring ID, two ports that are associated with ERP ring, and control channel or service VLAN ID. So for the node 1 in ERP ring 1, with this command, administrator defines ERP ring ID as 1, defines ports 112 and 116 as ring ports, and defines service VLAN or control channel ID of 100. Similar configuration for the node 7 in ring 2 would define ring ID of 2, ports 112 and 118 as ring ports, and service VLAN of 200, which has to be different than service VLAN of ring 1, which is 100. All the nodes within the same ring share the same ERP ring ID and service VLAN. Ring ports might change from node to node. In order to configure RPL owner and RPL port, administrator has to add the following command. Under the same ERP ring instance, one of previously defined ring ports would also be defined as RPL node port. In case of ERP ring 1, RPL owner would be ring number 6 with RPL port 111. For the ring 2, RPL owner would be node 8 with RPL port 117. Both RPL owners have also configured way to restore timer for RPL owner to 1 minute. Since this design uses one subring, interconnection nodes have to be configured to support two rings. So in addition to previously mentioned configuration details, nodes 2 and 3 requires additional command by which ERP ring with ID 2 will be configured as a subring with a subring ERP ID, associated single port, and ERP2 service VLAN ID. This completes configuration of ERP for this network. At the beginning of this session, ERP was defined as one of the protocols to be used in the core networks. As users would be connected to access layer nodes, there are several options for connectivity between access and core layers. In case we need to connect a single access node to a core node, LSCP protocol could be used, especially if core and/or access node is deployed as virtual chassis of two or more physical nodes. In that case, each physical link should be connected to a different physical node for increased redundancy. If supported by physical cable infrastructure, a single access node could be connected to two core nodes using dual home link technology configured at the access layer node. In this case, user VLANs could be divided over both active links, while in case of link failure, remaining link would forward all the VLANs. There is also an option of adding another ERP subring to form an ERP-based access layer. With this last slide of today's session, a big picture of the overall network is given with only some commands related to user data path in the network. So starting with access layer deployed at stations, users' VLANs to which wired and wireless users would be connected could be isolated per access node, such as VLAN 302, or could be shared between two or more access nodes, as in case of VLAN 301. Connectivity of the access nodes to the subring 2 nodes is implemented using DHL technology, where VLAN 301 is forwarded over green link, while VLAN 302 could be configured to use the other red link of DHL links in order to share load between both active links. Once at the ERP subring 2, that could be considered as distribution layer, user data will be protected by ERP2 control process until reaching interconnection nodes of ring 1, serving as a core network layer. From this point, user's data will be protected by ERP1 control process until reaching ERP master router, placed at OCC and serving as a default gateway for users connected to access layer. VRP backup router would be deployed at BCC. Here you can also see a logical topology of this network. Let's take a look at the ERP demo. In our lab, we will have 5 nodes. 4 nodes will be connected together in the main ring number 1, with node number 4 being a RPL node and blocking on the port towards node 2. There will be another node, node number 1. It will be connected to the main ring as a subring. And node number 1 will also be RPL node for the subring number 2. Also, there will be a station that is directly connected to node number 1. Let's take a look at the configuration of the switches with respect to ERP. We have nodes that are regular ring nodes, such as node number 5. Then we have RPL node, which is node number 4. And there are also 2 interconnection nodes, nodes 2 and 3. So if you go to regular ring node, like node number 5, we can take a look at the configuration. And you can see that both ports belong to ring number 1, which has service VLAN of 10. And you can see that ring state is in idle state, meaning RPL port is blocking and all other ports are up. Let's take a look at the node number 4, which is RPL node. Here, if you do show ERP, then you will see that this node is RPL node. But from this command, you don't see which interface it is. So you have to go to show ERP. Here, if you want to see some more details, then you can see that again, you will see that port 51 and port 52 belong to ring number 1. And here you can see that RPL port is basically port 1.1.51. If you want details on RPL port, you can place show ERP port command, and then you will see that RPL port is basically blocking on the RPL port. So it is blocking traffic in both directions. Here you can see that on interconnection nodes you have 2 rings configured, main ring 1 and sub ring 2. You can see there is only one interface configured to the ring number 2, meaning this is sub ring. You can also see that main ring has service VLAN of 10 and sub ring has service VLAN of 20. So those service VLANs have to be different. Both rings are in idle state, meaning for both rings, RPL node is blocking bidirectionally traffic on the RPL port. Let's take a look at the configuration. So this is how you configure interconnection node. Let's take a look at the statistics. So what do we expect if rings are in idle state? We expect that only RPL node will send out control messages with no request and RPL blocked code. So we should see statistics increase in this field. So because node number 3 is not RPL node, we will see that these control messages should be received. As you can see, network is idle state. The only control messages are sent out by RPL node and they are received. So it is no request, block RPL code within the control message. Since this is RPL node, we would expect to see no request RPL blocked control messages, but here under sent column. And yes, as you can see, these counters increase. We have a station that is connected to the subring, so it is connected to the subring number 2 directly to node number 1, and we should be able to ping it from the main ring on node number 4. As you can see, MAC address of the station is learned on port 1152 because port 1151 is blocked. As you can see, no MAC address is learned on port 1151. We will make a test now pinging this station, this end station connected to node number 1 in subring number 2 from node number 4. And during the test ping, we will disable one of the links. So we expect we expect ERP ring number 1 to converge, and we will see what will be a timeout for that. As you can see here, interface 1152 went down, and it took 11 milliseconds for the ring to reconfigure. So now, if you take a look at RPL, it should be in forwarding mode. RPL port should be in forwarding mode. So first of all, we see that the network is in protection state, meaning RPL is not blocking, but forwarding over the RPL port. As you can see here, RPL is forwarding. Let's take a look at statistics. What do we expect? According to the session, we expect that both nodes that are on each end of failed link, that both nodes will send out control messages saying that signal fail code, saying that basically link between them or link to which they are directly connected failed. And you can see here it is under column of sent messages because one of the node number 4 is also one of the nodes that are directly connected to the failed link. And you can see also that statistics under received column is increasing, and these are control messages that are received from the node on the other side of the failed link. So both nodes on each side of failed link will send a control message with SF or signal fail code. As you can see, at this moment, RPL node is not sending out any messages, any control messages. Let's take a look at the statistics on node number 3, which is interconnection node. So what you can see here that for ring number 1, we will receive signal fail message, control messages from nodes that are on each side, as you can see. So from nodes that are on both sides of failed link. Also, because this port belongs to ring number 2, so subring, and over there status of this ring is idle. Therefore, it will still be RPL node that will be sending out no request, RPL blocked control messages. One ERP ring should be in idle state and the other one should be in protection state. As expected, ring number 2 is in idle and ring number 1 is protection. Since this ERP ring is in revertive mode, now if we bring up again a failed link, RPL node should start blocking on RPL port again. So station is still learned on the port 1151. Let's bring the interface up. So interface is up, but we didn't see any longer timeout in ping response messages. The reason is that RPL didn't block RPL port immediately. It started wait to restore timer, which is set on 1 minute. And then only after 1 minute, we will see around 10 milliseconds of delay. Let's see in the meantime some statistics. So what we expect now, we expect to see no request control message sent from both nodes on the both sides of a link that is enabled again. As you can see, no request BPDUs were sent by both nodes, and then RPL node started to send no request, RPL blocked control messages out to the network. You can see that at the time when the network converged back, you can see that at that point it took again around 11 milliseconds for the network to converge back to idle state, meaning for the RPL node to start blocking on RPL port. And as you can see, network is back to idle state. As expected, RPL port is blocking again. I hope you enjoyed this session. Let's now close with some key takeaways. ERP is a mature and field-proven switching protection mechanism suitable for deployment in networks based on physical ring topology. It is supported by a wide range of Omni switches in our portfolio. And it might lack some features of SPB and IP/MPLS technologies, but it compensates on other qualities such as simplicity, fast convergence, and interoperability. Keep enjoying your Spacewalkers live event. I'm looking forward to interacting with you on this and other topics on the Spacewalkers platform. Take care and see you soon.